Hello everyone, this is the video lecture for Calculus 3, section 14.7, Mins and Maxes. This is going to be a little bit longer, but it's very, very, very important. So first off, let's establish some formulas. We got critical points are either going to be a minimum, a maximum, or a saddle. Okay. How you find them is f sub x equals 0 and f sub y is equal to 0. Now, it might seem really easy to just say, oh, you set them equal to 0 and you figure it out. Yes, but there's a key word here. It's and I'm going to even stress after all this, both. You must have both of them equal to 0 literally at the same time in order for this thing to work. Okay? You can't just take an answer from here and hope it works. It's got to work in both cases. So we're going to be looking at both of them as we go. Once you have your critical point, you need to still know if it's a min, max, or saddle. So then you do this second derivative test. So it would look like this. If you have f sub xx times f sub yy minus f sub xy squared greater than 0, then it's going to be a min or a max. And what you do then is that you break it down even further and say, well, my, I guess f sub xx or double x or whatever you call it, is greater than 0. You're going to find that that's a minimum. If you find that your f double x is less than 0, it's a maximum. You might recall back from Calculus 1 where your second derivative test kind of looked, it was opposites, like, why is it positive to make a minimum and all that kind of stuff. Same thing here. So kind of strange how that works. Here's the other one, is that we have f sub xx, f sub yy minus f sub xy squared is less than 0. This actually ends up being a saddle, and then you're done. So pretty interesting setup here. We got our main formula, and then we might have to break it down or not, kind of depending. All right, lots of problems up ahead. So we got 14.7.005. I have f of xy equal to x squared plus, xy plus y squared plus 5y. And they want to find the mins and maxes and saddles and all that kind of stuff. Very common problem here. Okay, so f sub x, go ahead and find it. We got our 2x plus y, and everything else cancels, set it equal to 0. Your f sub y, you have an x right there, you got a 2y, and you got a 5, and set that equal to 0. It's not that one is good enough. You have to have both working. So what I'm going to do is solve for y and say it's actually negative 2x when I move that over. So I'm going to take that and plug it in here to see what I get. And hopefully I can solve for x here. So we got a negative 4x plus 1 would be a negative 3x. Move it over and then divide 5/3 for x. That's not good enough, of course. We need to find our y. So my y would then be negative 2 times this stuff is negative 10 thirds. So there's my y. What I just found was I have a point 5/3, negative 10 thirds. That's actually a critical point. I found my critical point. And so now I'm wondering, is this a minimum, a maximum, or a saddle? And I would basically, on the homework, it has like maximum box, minimum box, and then saddle, and it kind of does a little weird thing, but eventually it has a box. Okay, so which one is it? Well, I would have to go through the second derivative test and blah, 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 blah. Or you can go back and look at the kind of function that we have here. If you kind of look at this and you stare at it long enough, it's actually a paraboloid. paraboloid. An elliptical paraboloid, in fact. So I don't know, it's kind of shifted over some, but let's just say it's something kind of like this here. There you go. It's kind of like a cup. So I have this cup sitting there. It's positive. If you can tell, there's positives all over the place. If you can't tell, it's going up. And so if I found one critical point, what would that be? It's right here at the bottom. It's going to definitely be a minimum. So I'm going to say that's a minimum. Well, we're basically done there. Except they don't want the minimum point here. They want the minimum value. And boy, is that going to be interesting. It's not hard. It's just always an extra step. And so they want to know what is f of 5/3 negative 10/3. Like in the original. Well then, 5/3 squared, 5/3 negative 10/3, plus negative 10/3 squared, and then 5 times negative 10/3. I mean, I'm just basically going back to the original here and plugging in a point, blah, 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 and I eventually get, in my calculator for sure, negative 25/3. So that's my value. And that's what they're looking for. So you would actually put minimum value negative 25/3 right there. You would put a DNE for the other guys. And, sorry about my alarm there. And a DNE right here as well. All right, cool. There's your answers. Let's move on. Let's do another one. Nope. Okay. Well, sorry. My notes were touching the keyboard here. Many distractions. So 147012. I got f of xy is equal to 5 minus x to the 4th plus 2x squared minus y squared. And they're wanting the same thing. What are the critical points and all the stuff? Da, 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 da. So f sub x, finding my derivative there, the 4 comes down, negative 4x cubed. And then the 2 comes down, makes a 4x. Good enough. Set this equal to 0. My derivative in terms of y, nothing, nothing, nothing. Right here, I got a negative 2y, set it equal to 0. It's kind of interesting because this one right here, you can factor out 4x, leaving behind a negative x squared plus 1, essentially. Still setting it equal to 0. Well, on this side, we got x equals 0, so there's something. Inside here, if you do the math, actually, that minus doesn't really need to be there. You can move out 2 negatives and make it easy to see. It'll be a plus a minus 1. On this right here, it only works at y equals 0. But remember that I'm saying it has to work for both. So if you had to make some points here, you would have, I'm not going to use p because I would use a whole lot of them. We got 0, 0. We got 1, 0. And we got negative 1, 0. So those are my critical points. I'm asking, though, what are they? Are they a minimum? Are they a maximum? You know, what's going on here? Well, last time I just looked at my graph, and I just knew. I'm looking at my graph, and I don't know. Notice that the 4th power's there. It kind of leaves me questioning what to do at all. Okay. So I'm going to have to do my second derivative test to be able to figure this stuff out. Let's first off find my second derivative in terms of x. So this guy, I'm going to take the next derivative of that one. The 3 comes down to make a negative 12x squared. And then, of course, over here we would have a 4. So plus 4. Kind of leave them hanging for a minute. My yy, when I take my derivative there, it's just going to be a negative 2. That's it. And then I need to find xy. And so xy is taking my x, and then I'm going a step in the y direction. I'm taking the derivative in terms of y. Actually ends up being a 0 here. That does not always happen, but it's, well, it happens here, so there you go. And I'm looking now to see, is there a function, this xx, yy minus xy squared, that basically I can use to see if it's a min, max, or saddle. So what I'm going to do is actually write it in a way that's kind of like a function. And they actually call this D for determinant or something like that. I'm not 100% sure, but They just call it D, and they move on. So here again, I'm just going to go ahead and distribute. So I got 24x squared minus 8. So this is kind of my function to determining if it's going to be a min, max, or saddle. Okay, so I'm going to use this on each one of these here. Notice that I'm only having to plug in an x. There's no y's to plug in, so I'm only really concerned about my x values here. So D, when I plug that thing in, I plug in a 0, I'm going to get a negative number. I don't even care if it's positive or negative. In fact, I'm not going to write it like that even. I'm going to just say this guy here is less than 0, and therefore that's going to be a saddle. So let me write saddle here. Okay. This guy, when I plug in a 1, the whole thing becomes positive, so D is greater than 0. That doesn't really help me much, though, and if I plug in a -1, the same thing, 2 negatives cancel, and I get a positive. So those are great, I get positives, yay, but I don't know if it's a min or a max. I have to then look at double x and see if that's a positive or negative. So double x, when I plug in a 1 right here, I should get a negative. And if I get a negative, then that's going to be a maximum. If I plug in a negative again, yet again, I should get a maximum. Okay, so I got a saddle, max, max. Okay, here we go. Remember that the homework is saying, hey, what's my maximum value? They're wanting a z value. What's my minimum value? And then for the saddle, it's actually really strange. They want to point x, y, f. And you have to actually put in a point here. Actually, you actually need to put in a point with your parentheses and everything in this guy. So it is way different than the other ones, yet you still have to find the value of it in the end. So what I'm going to do is go back to my original here, my f. I'm going to plug in 0, 0 and see what I get. So f at 0, 0, plugging it in, I get, well, 5. That's going to be important later. F of 1, 0, when I plug in a 1 for all my x's, plug in a 1 here, that's obviously a 0. 5 minus 1 plus 2, it should be a 6. And if you plug in a -1, 0, same thing because they're all even, you should get a 6. Okay, so maximum value. You can see how I got that value there of 6. Kind of break this up there. So they want that height, that z value. There is no minimum, so you put a DNE. And this one you actually have to type a point. It's kind of annoying, but you got 0, 0, and then what's your your z value is 5. And there you go. Next one. Basically, we have a whole lot of these. 147014. So f of xy equals x cubed plus y cubed minus 3x squared minus 6y squared minus 9x. Huh? And they're wanting to know what are the critical values, min, max, saddle, etc. So let's start to it. 3x squared minus 6x minus 9, set that equal to 0. For my y's, 3y squared minus 12y, set it equal to 0. Notice here that we can factor a 3 out. That is so handy. So that I can actually factor legitimately now. Minus 3 plus 1. So I'm saying then my x is equal to 3. And then x is equal to a -1. So these are important there. This one, again, we can factor out a 3y. And so then I got y equals 0, and I got y equals 4. Remember when I said both and both? It's kind of strange. 0, 4 for y's, 3 and -1 for my x's. Yes, we will actually have 4 points. Every combination that you can imagine. As long as your x's are 3's and -1's and your y's are 0's and 4's, we now have 4 points that we need to test. Okay, let's find our determinant. So I'm going to take my derivative of that double x, double y minus xy squared. So let me find out what those will be. So double x in this case is a 6x minus 6. Basically, I just took right here 6x minus 6. Easy enough. My y is double y. I bring the 2 down. I got 6x minus 12. Yep. 6y minus 12. And then my xy, I'm looking right here and saying, what's my derivative in terms of y? And it's 0. So it goes away. So this right here is my function, my d, I guess you can say, that I'm going to be using. And so what I do is I start plugging these guys into here, and I see what I get. So let me go ahead and just give it to you straight up. Here, my d is positive. Therefore, I have to look at my double x in particular and see what I get when I plug in my double x only with my -1 right there. It actually ends up being a negative, and therefore we have a maximum here. Okay. In this particular case, d is negative when I plug it all in. Therefore, automatically, that's going to be a saddle. This guy right here, d yet again is going to be a negative. So this will be a saddle. And then here, d is actually a positive. Whenever I do my double x, I get a positive. Therefore, this is going to be a minimum. Whew! Last bit, we need to have our actual values. So I'm going to plug this into the original and see what I get. I got here a 5. Over here I got a -27. Just plugging it into the original. Plugging those points into the original. I got a -27 yet again. And then I got a -59. Okay, those are your answers. We just had to put them in their correct spots. So max values, maybe? Min values. And then my saddles, again, have that point format. And we're going to have 2 different points, so it's going to be a little bit weird. So my maximum value is a 5. My minimum is a -59. And then my saddle points are kind of strange because I have to put them in XYF format. -1, 4, -27, comma, and then I got 3, 0, -27. Woo, man, that was a lot. Next problem is actually a little easier, but it's a more conceptual problem. So I got my f of xy is equal to 6ex cosine y. And they want to know what are my critical points. So f sub x should basically be the same as the original. And I set that equal to 0. F sub y, the cosine is going to be a sine, negative. Set that equal to 0. And again, you have to make sure that you're going to need both of them equal to 0 at the same time. So here's my question. Does the e to the x ever turn into a 0 right there? What about this thing? Is this ever 0? No. It's going to approach 0, but it can never actually be 0. Therefore, that's off the table. These, therefore, are important to us. I'm saying that cosine of y equals 0 and sine of y must equal 0. The same y value must get a 0 for x and a 0 for y. So I'm looking at my unit circle, and I'm looking for a point 0, 0 on this outside rim. And you don't find it. It's the origin. Basically, you can't find that. Actually, you know what? I'm not even... Yeah, that's exactly right. You're looking for... Ignore the y part. If that's confusing, just use like theta for just a second. Again, I'm looking for somewhere on this unit circle rim. Where do I have x and y points on the unit circle 0, 0? And you don't. It's not on the rim. It's like on the inside. So that never happens together. And so how do you write this thing? Well, okay, your first one is a DNE. Your next one is a DNE. And your last one is a DNE. There you go. Next question. Oh man, this is a big one. 14,7,027. So I've got sine x plus sine y plus sine of x plus y plus 6. And they give me some bounds. X is between 0 and 2 pi. Very good, thank you. And y is between 0 and 2 pi. Again, great, thank you. All right, let's find our partial derivatives. So x, I got my sine will go to cosine. That goes away. This guy right here, sine will go to cosine. And you're thinking chain rule, but there is no chain rule for this one because the derivatives are just ones. The 6 goes away, set this equal to 0. The next one, that one goes away, sine goes to cosine. And the same thing here, equals 0. I tackled with this for this. You need both, by the way, to be equal to 0 at the same time. I tackled with this one. I tried to work with it. I really didn't. I tried different things, and it wasn't working. So what I did, I saw that these were the same here, and so I basically moved them over and set these equal to one another. It's kind of weird. I said that, well, this one here is equal to a negative cosine plus or minus, and this one here is equal to a negative cosine plus or minus. So therefore, these should also be the same. Okay? Like A equals C, B equals C, therefore A equals B. That's basically what I was doing. And so what I'm getting at is that my cosine X is equal to a cosine Y. And can you guess my relationship here? It's that X equals Y. Now, it's not perfect for me to always say that. I wonder if there's an angle, two angles that have the same cosine values, both positive or both negative. And, well, that's correct. Basically, you have, say, like right here and right here at 60 and negative 60. You'll have the same cosine values, but then you got two different angles. So I'm not saying that they're equal to one another. They might be like plus and minus one another. But let's just kind of roll with the fact that they're equal, at least in some degree, and then we'll kind of work with that, okay? So right now, I know it's not perfect, but it's good enough to kind of get me going as we go here, okay? So what I did is I said, okay, well, let's then assume that I have x equals y. Let's go back then to one of those equations I had. Cosine x is equal to a negative cosine of x plus y. Well, then we can rewrite this as x plus x. That's 2x. And if you know any trig identities, this cosine 2x can be rewritten as 2 cosine squared x minus 1. Now notice that they're both negative. You could distribute and then move it over so that now they're going to be positive over here. Positive 2 cosine squared x plus that original cosine x over there. 2 negatives make a positive. Now you move it over to make a negative. 1 equals 0. Don't overstress it. It's really just a factoring. 2 cosine x. Cosine x. To be able to get a 1, you got to have a 1 to 1. One of them's got to be negative, one's positive, but notice that I have a 2 here. So I got 2x, 2 cosine x squared. I would get 2. There's a positive right there, right? It's a positive one. So 2 and then a minus 1 right here. Basically, the outsides and insides have got to agree to make that positive 1. Therefore, this is a positive and that's a negative. Blah, blah, blah. We just factored it. So on this side, I got cosine x is equal to a half. And on this side, I got cosine x is equal to negative 1. So how does this work? Well, kind of like I was showing you earlier, this one here ends up being at the pi over 3, the 60 degrees, and down here at 5 pi over 3. Notice again, go back to your domains way back in the original, right there. So that's why I'm not using a negative. I'm using just the positives. When is my cosine, my x value equal to negative 1 is over here. Again, that's at now pi. So there's my 3 different answers, kind of. I got x is equal to pi over 3. I got x. You know what? Let me even go further and say that this is also my y value. right? Because we had said that x and y were equal, basically. Okay. Phew. So now we got these, I guess you can call them points that I'm looking at. So now what? Well, we need to find out if these are mins, maxes, and saddles. So my xx, again, I'm going to just take my derivative of my x right here. Cosine goes to sine. Cosine's going to go to, well, negative sine technically, right? So they both got negative sine, so negative sine x minus sine of x plus y. Y. It's going to be the same kind of format. Cool. And then my xy, if you took my derivative of x and now made it into a y there, sine of xy there. Okay, great. So my d is looking really big. I'm not going to write it out just because I'm a little lazy now on that. That's okay. So I got this really big d, and I want to go and plug stuff in. What happens is that d simplifies a lot. You cancel stuff down. You know what? It's okay. Just start plugging them in and you'll get something. So, okay. Looking at my point now of basically pi over 3, pi over 3. I also have another point at 5 pi over 3, 5 pi over 3. And then I have the last point, which I said was at negative 1, negative 1. Okay. No. Not negative 1. It was pi, because my x value was a negative 1. Sorry. Pi. Okay, that's good. Okay, phew. So when I start plugging this stuff in, I plug these two in, and I get a positive. Therefore, I have to check my double x, and I get a negative. Therefore, this is a maximum. Finding my f value, I plug this into the very original equation. 3 square root 3 over 2 plus 6. That's going to be the value that we'll be using here in a minute. For this guy, d ends up being a positive. I have to check my double x. He also is now a positive. Therefore, we actually have a minimum on our hands here. When I go back and plug this thing in to the original, I get negative 3 square root 3 over 2 plus the 6. So there's my minimum value. And then this guy here, d actually equals 0. When you plug it in, it gets 0. And if you ever get a 0, it doesn't apply. But I still know that it's an actual saddle point. So what the book recommended, yes, I had to go look this one up, because everything else was kind of straightforward, but I went to go look this one up, and it was like, oh, but you need to plug in other points around the y equals x line, and eventually, blah, 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 it should show that it's a saddle. And like, huh? So, but just, yeah, it's a saddle, okay, you know this problem now. Therefore, it's pi, and then my f value, if you go and plug in the pi's into the original, you actually get a 6. So this is what goes in that last box. Box 1, box 2, box 3, or part A, part B, part C. Max, min, and saddle. Okay. Phew, that was a big problem. Like it was a lot. We still have a lot more to go. So this is a good time to stop. I'm going to pause this halfway. I'll make a part 1, part 2. So I'll do the part 2 here in a little bit. Thank you very much, guys.